For many students, synthesis is the hardest part of the course, and in section 12 of chapter 14, we want to start doing synthesis and review all of these reactions, remembering all of the stuff we've previously learned about alkenes, alkynes, alcohols, and so on and so forth, and now tack on to that epoxides. How do we make such and such from such and such? And flashcards are a good way to remember one-step reactions, and synthesis is a good way to practice multi-step reactions, 2, 3, 4 steps, okay? Now in the book, the author suggests that you do two things. You want to examine, is there a change in the carbon skeleton? Count the number of carbons and see, are there some missing? Are there some added? Is there a different skeleton shape? Is there a change in the functional group? And then go from there and identify what can it come from, okay? You want to think backwards, generally speaking, okay? So let's just jump into doing some problems. It's probably the best way to illustrate this concept. So in problem 1424A, we have an alkene, and we want to synthesize this molecule here. Okay, now you want to think backwards through this. Whenever you have an alcohol on one carbon and some kind of group on the adjacent carbon, you can think through the WTF analysis I taught with alcohols and ethers. So, for example, if you take this molecule here, you can think about it coming from okay, we're thinking backwards. We're playing a movie backwards, which means we're doing the curved arrow reaction mechanism here backwards. But this oxygen, if it's a negative charge, can be used to kick off this cyanide. So again, playing the movie backwards, this can possibly come from an epoxide and Cn minus. And this right here should trigger some memory, because you've memorized that if you have an epoxide, probably you have a flashcard that looks like this. I'll draw it in magenta here. If you had sodium cyanide followed by water, you will get this nitrile/alcohol functional group, okay? So what we want to think about is, starting from the alkene, how do we make an how do we make an ether, and then how do we go from an ether to the nitrile? So the answer is going to look like this. I'll draw it in yellow. MCPBA is a nice peroxy acid that can synthesize an epoxide. And then we treat this with sodium cyanide followed by water, and we'll get the target molecule. This molecule right here is the target molecule. Okay? So think backwards. Problem B. We have a diol. We have a trans diol. Okay? And in the book they say plus En. En means the enantiomer or the mirror image of that. Now, one of the reactions you've memorized in the first semester of chemistry is a method to take an alkene, and it's a two-step procedure to do MCPBA followed by water and acid, and that gives you the trans diol. Okay, so that's the last step of the synthesis. How do we go from cyclopentane to cyclopentene. That's going to be a two-step procedure, and you just need to memorize this. There's going to be bromine and light. That's going to give you the alkyl halide, not with the 6-membered ring. That would be too advanced. Yeah, cyclopentyl bromide. So that's how you incorporate a functional group handle into a molecule. And then if we treat this with sodium ethoxide or a base, strong base, we will get the elimination product, okay? So this synthesis involves, a few steps. Step 1 would be bromine and light. Step 2 would be sodium ethoxide. And step 3 would be those 2 steps, or that one transformation. In molecule C, we have 1 pentene being converted to a molecule with an alcohol functional group and a thiol functional group. Here we have 2 groups on adjacent carbons, so you could think backwards. Draw the O negative. And literally play the movie backwards. We would get that epoxide and hydrogen sulfide, which is a very strong nucleophile. So I think you can see the procedure we need to do here. We need to take our 1 pentene, treat this with MCPBA to make the epoxide, and then treat this with NaSH, followed by water. The neutral water. The water is there to neutralize the alkoxide and give you the neutral product. 1424D. Looks like the same thing, doesn't it? You're going to make an epoxide, and then we're going to have something attack, right? So let's try to do that. Let's add MCPBA. That's going to make the epoxide. And then let's add NaSH, followed by water workup. And this is not going to give us the product. It's going to give us this product here. Now, why is that? Well, this is a basic reaction mechanism. The hydrogen sulfide is negative. It's a strong nucleophile. It's going to attack the less substituted carbon atom in an SN2 process, okay? So the sulfur is going to be attached to the less substituted carbon. However, in the product, we want the sulfur attached to the more substituted carbon. So there's something else we have to do there. There's something different we have to do there, okay? So what can we do? Well, we can take this epoxide. We could try something else, okay? We could try something else. You could try converting this to a diol and, so on and so forth, okay? I don't see an easy answer right now. That's not like 5 steps. So I'm gonna skip to the next one. In this problem, we want to look at the carbon skeleton. 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, So there's no change in the carbon skeleton. There is a change in the functional group. We're going from an epoxide to like this ketone. Like, whoa, that's tremendously different, right? But here we want to think about how can we synthesize a ketone? We can synthesize a ketone from an alkyne, but that doesn't look very related to an epoxide. We could synthesize a ketone from an alcohol. Remember from chapter 13? And bingo, you should be able to remember that on your flashcard, you have a reaction that can take you from an epoxide to an alcohol with reduction. And there's a one-step reaction to go from an alcohol to a ketone. So let's stitch this together in the forward way. If I take an epoxide and treat this with lithium aluminum hydride, followed by water workup, I'll get a secondary alcohol, 2-pentanol. Now 2-pentanol can be converted to this ketone where the ketone is at the 2-carbon by the use of PCC or Jones reagent. I'll just use PCC because it's 3 letters and it's easier to write than Jones. So that's a 2-step procedure. Each one of these one-step reactions, you need to have it on a note card, flashcard, and go through them often, okay? Now let's talk about Grignard reagents. Grignard reagents are tricky, very, very challenging to work with because they incorporate additional carbons to your molecule, so they increase the number of carbon atoms as well as changing functional groups. So there's 2 things you need to watch out for. I think it's easiest if we just take a look at some of the problems in the book. And this is a worked problem, but let's do it in a couple different ways. So this is the molecule that they show in the book, bromocyclohexane, and we're going to form a ketone. So there's 3 new carbons there. I'm going to show you 2 different ways to do this, and it's okay to propose 2 different ways unless the problem specifically says you can't use a reaction from chapter whatever 9 or something, okay? So let's take a look at this. I kind of hinted at this before. We've learned that there's a couple of different ways to make ketones. We can make them from alcohols. Alcohols can come from epoxides. We could synthesize ketones from alkynes. Whoops, let me put in another carbon there. Okay, I was thinking originally I wanted to cheat and show you how I was going to use, well, that would still work, I think. Yeah. Would it? Would have to be that one. Okay, so this can come from the starting material that's provided to us. And so let's look at how this can be done, okay? So remember that alkyl halides contain a halogen, which is a good leaving group, and we can treat that with acetylides to increase the number of carbon atoms. So if we have this acetylide, remember that the terminus of that triple bond, that carbon atom, is going to attack this carbon and kick off the bromide, and that's going to give us a molecule with 3 more carbon atoms. Okay, and then in a very, very poor yielding reaction, we can treat this with a couple of different reagents, mercury, acetate, sulfuric acid, water, and get us the ketone. Now the problem with this reaction is that the ketone could go on the left carbon, or the ketone could go on the right carbon, which I would predict about 50-50 chance, maybe a little different. Obviously we want this molecule here, but you have significant amounts of side product, okay, because there's no way to control this. So this route, although it's okay, is really poor yielding, okay? So how would we synthesize it by this method here, okay? Now the thing we want to do is use that WTF analysis. I'll show that in green. We can draw the alkoxide. Okay, that's the writing step of the WTF. And then you want to think carefully about which group to kick off. So now we do the fragment step, or the F. So here we go. We want to fragment this molecule by thinking backwards in a very awkward, unnatural way. And this could come from some kind of carbanion and then an epoxide. Okay. Now the thing you need to remember is that carbanions are another form of a Grignard reagent. So let's take a look on the next page. It's a little bit sloppy here. So I want to take this alkyl halide and convert it to the Grignard. That right there is a carbanion, okay? Once I have my Grignard reagent, I can treat that with a ketone. That's going to be your propylene epoxide, okay? And this carbon, if you think about it, this carbanion is going to attack the less substituted carbon atom. Okay, it's going to attack right here and kick off like that. So step 1, add that. Step 2, add water. I can't work through all the mechanism here, but what that's going to give you afterwards is a new carbon-carbon bond between this cyclohexyl group and this carbon of the epoxide. Okay, I've dotted my carbons so you can see which two are becoming bonded to one another. And you can see how the alcohol is right where you need it. And then we can treat that with PCC, and then we're done. So this is literally a two-step sequence of events. Step 1 would be, your Grignard reaction, and step 2 would be your oxidation reaction. So this right here is a very simple two-step reaction. It's not easy to see. Our next reaction is this one here, okay? And this one's a little bit trickier because, the bond you want to form is this one here, okay? It's this one here. So what are you going to do? I'm thinking it could come from an alcohol. Okay. And here is where I'm going to go to the WTF analysis. going to write the alkoxide out. I'm going to think, all right, now I don't want to make an epoxide because that would kick off a methyl group way over there. I don't have a methyl group. I have this cyclohexyl group. So I'm going to kick off the cyclopropyl group. I can do that like this. So that's my think and fragment step. WTF, I call it. That's going to make my carbanion and an aldehyde. Okay, so remember, Grignards attack epoxides. Yep, that's great. They can also attack ketones and aldehydes. So here what I want to do is I want to take my starting material that's been provided to me. We'll go ahead and make this the Grignard. Okay, got my Grignard. Now I'll treat this with propanol. We haven't named aldehydes yet, but that's propanol. This will make my alcohol. And then I can oxidize that using PCC or Jones to the corresponding ketone. So that's quite challenging. That's quite challenging. Let's see what else is in the back of the book here. See if we can do some more problems. Propose a synthesis. Problem 1451 is crazy, open in the air. So you've got many different types of synthesis problems. Some are just filling in the blanks. How do you go from A to B? And some are how do you go from A to F? And they don't tell you any information at all. But most of the synthetic steps in the book are between 2 to 3 steps. There might be 4 steps, okay? So try to work on those. I hope I've given you an idea. You really need to think about all of your different reactions and have them on the tip of your hand in the form of flashcards. You can very quickly refer to it and pull it out of your memory. So then you can basically be solving a maze in your mind. Otherwise, you'll have to be flipping through the book. What does that reaction do? How might this reaction work? Okay, so try to catalog, organize reactions, get flashcards, and then hopefully the synthesis problems in 1451, which goes from part A to part U, believe it or not, could be more solvable for you. Okay.